Should I go? Yeah. Okay. So I'm going to take just a few more minutes to discuss issues related with the searches, and Yan is going to go in detail over quantitative details of the sensitivities, and then we're going to switch to parameter estimation. So this is the search for all-free data. These are the candidates. And I wanted to say a few more words about how we estimate the time of the sharp breakout. And because not every light curve is as well sampled as 2023 IXF. So currently we are using a quartic polynomial interpolation. And people might say, well, if you want to use, and what we do, we take the homologous phase of the light curve up to the peak, just because the shape is fairly universal between different core collapse supernovae. And if it's sufficiently sampled, we do an interpolation, and we use that interpolation intersecting with the luminosity before the sharp breakout, before the beginning of the light curve, to find the time of the sharp breakout. We decided not to use the simplest possible polynomial, which is quadratic, is because the shape is better interpolated by a quartic polynomial. One of the things that we are interested in understanding is that if we should use a physics-based curve to do this interpolation, and I know there is work by Nagy and Waxman. The tricky thing is that is what seems to be so-called spherical cow approximation, where I'm not sure how rigorous it is, but this is one of the things we're trying to understand, and maybe Chris will enlighten us too in how to distinguish between the different physics-based interpolation on the market. These are also windows. So here is related to the question, Jade's question earlier. What is the benefit of a shorter on-source window if we have a week, a day, a second, or a fraction of a second? And so the key message is that the false alarm probability can be calculated in Poissonian terms as the probability to have at least one false alarm. So it's 1 minus the exponent of the on-source window multiplied by the false alarm rate. If this quantity is small, in first approximation is false alarm rate multiplied by the on-source window. And so if you reduce, for example, the on-source window by 5 orders of magnitude, then you have a choice. You can have the fixed candidate, and you're going to have a false alarm probability that is 5 orders of magnitude smaller, or you can keep the false alarm probability fixed and have a false alarm rate that is 5 orders of magnitude larger. And so which of the two, or which combination of the two you should go for, depends where is your previous cut located, meaning that if you have an all-sky search cut here, and you are able to reduce the false, you can tolerate a larger false alarm. What's going on is that you are able to accept much smaller SNR, and you have a benefit in the range. But if you're in the Gaussian region, the same increase in false alarm might give you only a very small improvement in the threshold in SNR. So how to use this benefit depends where your loudest event is, if it's in this kind of glitchy region or if it's in the Gaussian region. So these are the detection ranges for a free, and Yan is going to say more. Pretty much they divide in 3 groups: the slowly rotating, rapidly rotating, and after the conversation I had with Martin in the corridor earlier today, I have hope that some of these rapidly rotating will move to the right, and these are some of the we call them extreme emission model. There is the failed supernova scenario where a chunk falls back that was provided by Tony Pyro, and then the long-lasting bar mode that Pedro has recalculated for us. And some of these extreme emission model are things that we are already able to rule out. Here there is a comparison with the all-sky search that I'm going to skip. We also produce in the search upper limit in the energy, assuming omnidirectional emission. And as I said, we also produce model exclusion probability if we have multiple supernovae. And the idea is that, if we have, for example, a detection efficiency of 50%, and which has to include also the fraction of the on-source window that doesn't have data. So the 1 minus 50, this is the chance you miss it. And what is the chance, given a certain emission mode, that you miss it in all supernovae, is this product. And 1 minus that is the chance that you would have to observe it at least once, no matter what. And so with this kind of calculation, we produce a model exclusion probability for specific and extreme emission model. Okay. Oh, and the last comment that I think Marco Drago will cover is that there are two attempts of thinking outside the box in terms of searches. This one is from Ocon and Marco Drago and others and Irene if you have a neutrino signature from SASE, use that to increase the detectability of the signal itself. And then there is another one that I wanted to highlight. This is posted by Kai Schlitterman, and it's going to be, can we use population of weak events to be able to detect confidently the presence of gravitational waves, even if each of them separate is sub-threshold. And this is in line to the way the Higgs boson was detected, that was not the loudest event, but it's because the distribution of event was different than what was expected. Okay, parameter estimation. And so we have been talking about this already before. There are pretty much two steps. The first step is trying to identify deterministic features. And the second step is how can we interpret these deterministic features in terms of what we think are the physical ingredients. And this is going to be, I hope, where we can use this workshop to streamline more the work. And so the one, briefly, what has been already mentioned, there is the prone convection and core bounce. And then we have this the high frequency feature, and which could have some truncation. And if the black hole is formed, maybe the truncation could happen even with SASE, memory, spiral SASE. And I think at this conference there are presentations involving almost all of them. I think there is Vincente and Zidu will talk at least about this one. I know Daniel is talking about this one, Coulter. And I think Sophia has a poster on the prone convection, two presentations, the core bounce, and I think Fornes is probably talking about this one. And the key thing from the point of view of us is, we can only provide you features of the spectrogram. What can we do? And using the feature of the spectrogram in terms of frequency evolution and temporal separation and maybe polarization. One thing that I just wanted to highlight off the bat is that the reconstruction capability will be frequency dependent because of the noise properties. This is a paper where we try to look at the fitting factor reconstructed by coherent Webers for, if you take some waveform from Ocon, Anderson, and we have as a function of SNR, and if you take the whole waveform, if you take the energy above 250 hertz and below 250 hertz, and as you can see, the construction of the energy at low frequency is poorer than the one at high frequency. So For the high frequency feature, I'm not going to say too much in terms of what we can do. I'm going to list the questions, and hopefully we can use the discussions. So what are the deterministic features that we can try to establish? The starting frequency, the initial slope, and there is also a reason why the papers we publish were focused on the initial slope is because the reconstruction of the coherent display coherent waveburst was not going above a few hundred hertz, and we realized that there was no way to track the curvature, for example. But now I think the most recent one, we can go up to 2000 hertz, 2100 hertz. So if we start adding the curvature, the value of the asymptotic frequency, can we try to resolve some of the ambiguity that was highlighted? I know when Pedro talked about that, not only we have a different equational state, we have the mass of the progenitor, accretion. I don't think the ambiguity with the degree of rotation is going to be a problem, just because they're going to be much rarer, but also because it should be fairly easy, even from the core bounds, to tell that it's rapidly rotating. But I know these are the main thing. And now one thing that we discussed in the last few days also was, I know, for the asymptotic frequency, can we learn something about the mass of the proto-neutron star with asymptotic frequency? What can we learn about the possible black hole production from the truncation frequency? We don't expect to have any polarization here, so the current network doesn't have limitation. So that's what I wanted to highlight here. The other thing I wanted to highlight, and this is related to a comment of Tobias, I don't know if he's here, is that I know the results from Alejandro, they were highlighting that under certain conditions, this paper is with all free data now, we should be able to resolve the different bands better. I know we are able to, we took all the different possible slopes, and we are able to tell if it's more one slope or another. But currently we are operating with a discrete number of equation of state. And so during the previous workshop we are here in Warsaw, Tobias was pointing to me that in reality you can have a continuous range of equation of state. So how do we interpret in terms of a continuous range of equation of state instead of just choosing between discrete equation of state? So for the SASE, I know we, as we talked about, and there will be two presentations about it, I know there is the frequency, the duration, and the polarization. And one of the things that we have currently in the algorithms that I would be interested in hear opinion of different theorists is that currently the way we do the detection of the SASE is that first you identify the position of the G mode, and then you take a region that we call the SASE region that is about 50 milliseconds starting and below 200 hertz. And then what we do is that we take one of those coherent display events, and we calculate how much energy is in the SASE region with respect to the total energy of the event. So the relative amount of energy is the metric to choose if you think there is SASE or not. But I know the debate, I know the decision of what is exactly the SASE region is something that I would like to review, because all we did for this paper was just to review the literature. And this has been done both for gravitational waves and for neutrinos. And we even combining the two, this is a nice result, because it shows that the combination of the two was better than the two separate, even if this result will change as the science run move along. This is an example of the accuracy in estimating the frequency of the SASE. These are results for, as I said, for data from 2022. The performance that you see now here in this plot at 1 kiloparsec corresponds roughly to the one that Vincente is obtaining and is showing in his presentation at 10 kiloparsec. So this one you'll see is roughly where we are at 10 kiloparsec. Then there is the feature of parameter estimation for the core bounds component. And here, one of the things I wanted to talk about is that Richards is the first one that said that this should be templatable. And Valencia is an effort where they use somehow existing waveforms as template with a stretch in time. And this is a brute force effort to actually use a phenomenological analytical waveform, and where the free peaks they have a dependence with respect to beta. And this is something that was motivated by a scatter plot that you can find in the paper by Richards and by Mikhamov. And yesterday I saw a few more of these waveforms. One thing that I wanted to point out about this waveform, and it's something that came up in the discussion with one of the reviewers of one of our papers, is that the fitting factors that you get between templates and the waveform are like 95%, and because there are some irregularities, and one of the reviewers said, well, in the CBC world, people use 99%. How do you deal with a fitting factor that is this low? And just a week ago, Emmanuel, that is giving a talk on Friday, he took the new database for the core bounds from at Bikhamov and compared that with the fitting with the database from Richards, and it was 95% fitting factor between these two databases in the noiseless case, which also make me think, okay, it's comparable to this, but now what do you do if you have a 95% fitting factor between two different databases? So one of the things I wanted to understand is that, what do we do when we have different modelers that produce something that is slightly different, but maybe not too much? How do we interpret that? And these are examples of performance in estimating beta. And I'm not going to go too much in detail. All I'm going to say is that when you have a templatable waveform, you can also produce theoretical minimum, which is the Kramer lower bound, and you can actually compare yourself with the optimal. This goes back to the comment I said at the beginning that in the single interferometer ideal scenario, you actually have a specific metric of how close you are to optimality. And this is another thing that is a point of discussion for this conference, is that I know the Mike Pacquios tried to do simulation of the neutrino emission for different value of beta, and he got pretty much the same amount of emission. And this is one of the things that I think would be nice if in a discussion we talk about which of the features we think might have a distinguishable signature also in the neutrino. So for SASI, we know that it's worth checking the signature in the neutrino and gravitational wave. I suspect it's the same for the high frequency feature, even if I'd like to hear opinion from the theorist. For the case of the core bounds, at least the opinion of Mike Pacquios is that there's not going to be much difference between the two, but I'd like to hear a confirmation of that. And then there is the concept of the memory. And so I'm going to mostly focus on just saying what are addressing the comments that were addressed yesterday from Coulter presentation. So and also comments from previous presentation. So the first comment that I heard was if you want to study and I think it was from Bernard, if you study the evolution, you need to produce the waveform for several seconds, tens of seconds. Well, in reality, you need to produce the part of the waveform that has energy in the band that is sensitive for LIGO. So when you past this point, continuing, only add energy that is outside the band that is of interest for LIGO, which is above 10 hertz, is not going to change that much. It is true that the usage of waveforms that are truncated require to have some kind of tapering. This goes back to the comment that Marek said yesterday that we need to have waveforms that don't produce artifacts in our data. If someone just inject that with a step, our detectability jumps because the step produces high frequency. So all the waveforms we inject, they need to have some tapering. The second comment is that if you take this trend, they do something that decays, the question is that even if the peak frequency of this ramp up may be 1 hertz, does it decay slow enough so that the noise decays faster? So this is just the same comment, and so these are, and the other thing that I wanted to address is that what the work author did, what it proves that this signal can stand out. It doesn't prove that we can reach detection confidence to make it a search. For example, if we already detect the gravitational wave, we can try this follow-up to see if the gravitational wave contains the memory or not. If we want to make it a search, we have to process much longer chunks of data, and that's what people are working on. Oops. Okay, the other thing that I wanted to comment is to point attention of Gerardo Urrutia presentation later in the week, because this type of memory ramp-up signal can reach much larger values for different kind of signal that maybe special type of supernovae. If you look at the order of magnitude, we would love to have something like that. And one of the things that we already talked about at the conference is to understand what is the possible volume distribution of these sources, because if it would become of interest, then it could motivate a search by itself. So go and look at the talk by Gerardo. Okay, a few words about model selection. And this is the effort that Jade and others have been leading, the SME effort. And this is based on trying to distinguish between rapidly rotating and slowly rotating progenitor. It's a very promising direction. I think the important point for this kind of approach is to make sure that we have a sufficient amount of waveforms so that we know that we are testing things in a way that is robust. This paper, for example, had maybe a handful of each kind, but if we would have a more robust database, and so in that regard, it makes me even more curious about the presentation by Martin. With this, I close it. And please take this as a pointer, because the presentation that Sergey will give and all the people I pointed out, these are, once you see all the presentation, we'll have a complete picture. This is more like a roadmap.
So I know you're all thinking hard about your questions, but who wants to go first? Save Michele from my questions.
Michele, thanks a lot for the talk. I was wondering, the last plot that you showed regarding the test between this one, what kind of waveform are they used for this?
Wait a second. Well, this was a Jade paper with the Vigneroma, so she can answer the question.
It's a really old paper that we've redid the study about 5 times since then. So.
Oh, so I should have used a more recent one. So I'll.
Well, I'm glad you mentioned my work anyway, even if you picked an old one. So, but yeah, maybe better to look at the latest one that uses more modern waveforms.
Yeah, sorry. That is a clear indication of what has been added the last minute.
Have to keep going. So great. Obviously, I'm involved in a lot of this, so I'm happy to hear it talked about. But my question for the room more than anything are, what are the plans for the next sets of detections? So, you know, at that point, hopefully Cosmic Explorer, Einstein Telescope are going to be on at the same time as the current LIGO Virgo, Kagra. How are we going to kind of combine these different detection networks?
So
I have to give you a hard question.
sure, no, it's okay. So, well, I think there are, I know, there is a administrative question in terms of regulation, and then there is a physics question. I know one of the things I hinted is that, for example, is if the morphology, if we have something that is 2 sigma and the morphology looks ugly, should we decide internally if it's a supernova morphology or should we consult other people? That's one question. In terms of administrative thing, one of the things we have always advocated internally is to have a plan in place that jumps activate automatically, because everybody I know will come up, for example, with oh, I want to run my algorithm and be in the initial paper. And so we have been talking about that has to be a reviewed algorithms, and then you can go in the follow-up paper. One of the things that will complicate the situation is if it happens in the transition of with IGWN, what is going to happen. But I think we have people that are chairs of groups here that can comment more of what this audience should expect. And in my regard, I actually have a question. How should the interaction between the 2 communities evolve as we go in the IGWN era? And if the LIGO lab stays as a single thing and everybody's out, then maybe this kind of meeting will be the norm, but I don't know. So I think Jade is probably the right person to comment on this more than me.
I think we've already had some volunteers to host Supernova 2026 GW, so I'm definitely hoping it'll be a series of events. I don't know if anyone else wants to comment.
Okay.
I'm interested in the glitches because I think that our supernova searches could be more sensitive than they are now. And we also have a problem that about 20% of the time there's only one detector on. And at the moment, one detector search isn't viable just because of the number of glitches. So what can we do to, how should we be working forwards to try and reduce glitches in supernova searches?
Yeah, so that's it's a wonderful question, and the reason, and I'm going to answer, the reason why I didn't do any systematic is because in the last few days I saw the presentation from Sergey, and I really like some of the things he's going to discuss there. So I don't want to steal the standard, but let me say some general comments. So first of all, I know, and this is for the theorist, every time we increase the sensitivity, meaning we lower the Gaussian noise, I know we are at risk to get new population of glitches that come up. That's one comment. The second one is that I think it's unfortunate that we don't do more specialized glitch classification for supernovae, meaning that there is I think there should be more glitch classification that focuses on, and there are efforts, but I know not in a detector categorization group. And personally, what I've been advocating, for example, given the memory, to start a specific supernova glitch classification, the 10 to 20 year span, because it's relevant for the supernovae. Currently, I know we have this problem with the blip glitches, which in some regard, I know, have a shape that looks a little bit similar with the core bounce component of the rapidly rotating. Fortunately, in that case, the time scale is different because the blip glitches are longer than that. But the core bounce component of a supernova could be, as Marco pointed out, very similar to high mass, intermediate mass black hole that are just free cycles. So we may have a situation where we are not sure if it's a core bound component or is a high mass. But I know I think we just have to take as many volunteers and encourage people to do it. I know we had the papers that machine learning papers. Marco has been authoring a couple of them. I've been authoring some to use machine learning. But I feel that it has to be a constant effort, because you want also to understand as much as possible the physical origin, because the ultimate solution is go back to the hardware and remove them. And the tricky thing is that there's no solution that always works, because you start with a noise here. There are certain type of glitches. You cure them. You go down. The morphology is different. The mechanism is different. You cure them. You go down, and so it is what it is. So.
Given that we are saying that then, a reasonable detection range is the galaxy, and we assume that we will have neutrino detections at the same time, isn't a more pressing issue not glitch redirection, but what happens if we have a signal overlapping with a glitch?
If you have a
signal that overlaps with a glitch.
You mean a glitch that overlaps with detection?
Yeah, isn't that a more pressing issue than having to deal with removing glitches, since we already kind of will get the timing information from the neutrinos?
See, okay, so that's an important point. So we have already effort to distinguish the glitch that is overlapping with the signal. I think the binary neutron star had a glitch overlapping with the detector. So I think Bayes wave has effort to do that. Querying wave boost has effort to do that. So I think there is some attention to that. The tricky thing is that the morphology is identical. The other comment is that when we talk about glitches that are an issue for detection, we're talking about things that are every few hours, and something that is, 10 milliseconds every few hours. So the likelihood that a glitch is on top of a signal is not very high. In the case of the binary neutron star, for me, is spectacular coincidence that was there. So, but Sergei has actually something he's going to say.
Some glitches happen at low frequency. Yeah, to what just Michele said, I can add that most of these glitches are happening at low frequency. And if you look at frequency band above like 200-300 hertz, then it's much quieter. So it's not like a huge problem. Okay. And actually, this may address, the issue what Jade is also raising here, that how we can fight all these glitches. Again, this only an issue, the issue when you kind of look at everything. We look for all kind of possible supernova signal, including a small speck, something happening somewhere in the data. And I think that this is kind of wrong approach, because right now people have much better understanding how to simulate the signals, and this input from theorists which is coming to us, it's very important, because we can limit the range of possibilities, what kind of signals we are looking at. And if, for example, if you look at these classical events, which what Michele discussed here, there is no way you can confuse this with a glitch. So it's not like a huge problem.
But another thing, just to add to that, and this is to expand to, is, if you look at the literature, sometimes you have a theoretical detection papers or parameter estimation. I could do this, I could do that. And sometimes are papers where they don't have glitches, simulated Gaussian noise. Maybe it's just people that call it data analysis, when they are just comparing different numerical waveform without even noise. And they are good to identify an area of interest. But then you want to put in real data to see if it actually works. So precisely for the fact they want to see how they deal with the non-Gaussianity of the signal, of the noise.
Yeah, I just want to finish.
Sure.
So, and, of course, you know, particularly if you have neutrino signal, which like for next generation of neutrino detects, probably we will see it pretty far away, like 1 megaparsec or close, right? Then it will totally eliminate the problem of glitches for supernova in our galaxy, because it's going to be just one time stamp which is available. For extragalactic supernova, we just can hope that nature is more generous to us.
I think Einstein's telescope might have unique challenges with glitches, because being interferometer collocate, if you have some seismic wiggle, I know we might have lose some of the discriminating power. But anyway.
Yeah, so maybe this is a question for Sergey. Like you said, we know that most glitches don't look like the dominant mode that we see in core collapse supernova simulations. So can we do something with CWB to look specifically for that aspect of the signal to help reduce the glitches?
We already do this in LIGO by looking for like binary black holes with unmodeled algorithms, and just realizing that there is a very specific structure of signal without even looking at the template. You just look at one parameter, basically how frequency is evolving with time. It removes, you know, a huge number of glitches, right? Yeah, I think that the problem here is mostly because we can see, at least in the analysis, when we do analysis of LIGO data, we consider so wide range of supernova signals. And if you really think that all this is possible, then indeed this is a problem, because how you can distinguish, you know, very short supernova signal from a blip glitch? Okay, this is a challenge, but I think that the range probably of the signals which we expect is much kind of more narrow, right?
You are assuming that 2 interferometers are on.
With the T, effectively, we have 3 interferometers. But right now, 2. Not 2. No. 1 interferometer. If you have Cosmic Explorer and the T. No, I mean now. Oh, now only 2, yeah.
Well, right, she sent an email yesterday saying no cuts. But
Okay, Christina has a question.
Thank you again for the really good talk. So I have I guess kind of an arbitrary question. So if we have a detection, right, like how do we know we have accurately reconstructed the signal? So I guess, you know, how we standard like test a pipeline is we inject signals and recover them and kind of calculate the overlap. And like, is it, if we have a detection, does it necessarily mean that the overlap is good enough? And what do we mean by good enough? Is like an overlap of 0.5 good enough, or like 0.8 good enough, you know, and if we have a real detection, how do we tell?
We can inject artificially the data, meaning you take a vector, you take the waveform, you add it, you apply the algorithm, and then you reconstruct it, and you can compare the two visually. That's one example. The second one, we can do hardware injection, where you, with a magnetic actuator, you actually shake the mirror, simulating that certain effect, and then you see if what you get in the data. These are called hardware injections. So these are 2 things you can do. Good enough. I know we are not trying. Even if it looks roughly okay, we would be extremely excited. We are not. It's like when you have the first television that is fuzzy, but you say the image of someone on the other part of the planet. I know you are not saying, oh, I want to crisp the first one. Just give me something. I know. I don't know if Sergey wants to say something.
Yeah, just quickly. When we are talking about detection, we are not thinking in terms of overlap because it does not exist. There is no any template we can overlap our data with. And
I think she means how close to the actual physical wave, not in terms of overlap with the template.
Okay.
Yeah.
Yeah, I think that if the signal has SNR at least more than 15, then you're supposed to see Gmods. Yeah, something like that.
Okay.
I guess if we'd reconstructed it badly, then it would show up in residuals.
All right.
I said if we've reconstructed it badly, then there would be some, we'd see it in the residuals, right?
No. If there is a residual, it means that this is not an event, it's a glitch. Because by definition, when we have a gravitational signal coming to us from space, and we reconstruct it with like more than one detector, then the residual is what we call chi-square. This is consistent with Gaussian fluctuations. Did I answer your question? Yeah. Okay.
Yeah, I was just trying to, Sergey, hold on to the mic. I was just trying to understand the comment you made earlier about potentially for supernovae that we have a problem in the sense that the range of possible spectrograms, if you will, is broad. I don't think that's the case anymore, right? I think you did indicate that things are seemingly more narrowed down now, but I was just thinking of, wondering in your experience in terms of everything you've seen, what have you seen that's very different from what has become the canonical signature that all groups are seeing now with the high frequency feature and the low frequency SASE and the memory and all that things are, so some of the same, there are distinct features as you and I were discussing at the break that are robust at this point. And that should much as in CBC case should help, no?
Yeah, so let me kind of explain, what we are talking about here. If you look at all LIGO publications, then the supernova searches are performed what we call within what we call the all-sky search for generic signals. This includes everything. Gaussians, sine Gaussians, pretty much anything you can think about, right? And all the numbers which we are quoting, it's coming from this analysis. And I agree that maybe in minds of modelers who is working on this problem, the range of possible signals is relatively narrow, but not for people who is doing analysis. Okay, so, and this is why I think that it makes sense to rather develop a dedicated supernova search than to search for everything. Right. Once you start to search for everything, of course, you will find a lot of stuff in LIGO data. Okay, yeah. Okay.
But I mean, I think we know enough now, maybe to your point, that we should stop searching for everything, and have it, I mean, as far as supernovae at least are concerned.
Yeah. Of course, it's kind of hard, at least for me, to estimate what is the possible range of all models, including kind of the crazy ones, right?
Yeah.
But this search, which is usually LIGO is doing, it's a search for signals which are relatively compact, in the sense that the average time width multiplied by average frequency bandwidth It's small. Roughly, it's like 10, 20, something like that. These supernova signals, so what we are looking at, they have a time frequency volume like 500. And it requires totally different approach, you know, to look for these signals compared to what we're doing now.
Understood. Thank you.
Personally, I think we should have both a supernova shape specific search and a everything search, just in case we've got all the theory wrong.
I agree with that, Jade.
So I think we're out of time now. So let's give Michele a